So let's get started. So welcome to our fourth session of TF Club. In our last session, we talked about how to use pre-made models from TF Estimator, and mainly we focused on how to use with data in memory, like it can be pandas data frame or NumPy array. And today we are going to talk about a couple of real-world issues, like training on large out-of-memory data sets, and also on distributed training and how to deploy our models for inference. So the deployment mainly will focus on how to deploy it to Cloud ML. Okay, so to train on large data sets, we use a dataset API. The Estimator API has a dataset API. We are going to see how we do it. Okay, so as I said, these are the aspects that we are going to cover for today: how to train using data out of memory, how do we handle distribution, and also how do we evaluate our model's performance, how do you monitor it during training, and how do you deploy it. And the dataset API can be created. The dataset API helps us to read data progressively from data in disk in different formats, and it creates tensors from using these functions from the dataset API. We have text line dataset, which can be CSV or other text delimited datasets. TF record dataset. This is binary format, and it is optimized especially for TensorFlow, and it takes less space in disk, and hence because of that, copying and training takes less time. So when possible, using TF records dataset is recommended. There is also a fixed length records dataset that reads fixed length from binary data, it says. I have never read it, so I don't know what it is in detail. We can also include our custom kind of code to read from different kinds of data sets using the dataset API. So in this case, we are loading progressively, and our data doesn't have to reside in memory in this approach. So the dataset API generates input functions for the estimators, for the different pre-made estimators, and shown here is an example how we do when we have large CSV data, for example, and when we don't want to load the whole of it to memory. So last time we saw, once we instantiate a model, let's start from the bottom. Once we instantiate a model, we use model.train, and to model.train we pass the input function that reads data, but the input function should be written in this way, like it should pass data to the TensorFlow graph, and in this case, to read the data from CSV files, we use the text line dataset from TF data. And what this is doing is it is reading the lines of the CSV files simply as strings. And once we read the CSV files, the CSV text lines, we have to pass it to create features and labels. That is why we use this map function here. So we have another function that passes each line to features and labels. So what we are doing here is we use the TF decode CSV function here, and it decodes the record, each record. So each record is a line of example shown here. We have the property type, square footage, price that we saw last time. So it is reading each line as a string, and we want to parse it to features and columns. And to TF decode CSV, we have to pass the default values, like default values for each column. So in our case, we were predicting house prices. That's the last column is our level, and we have square footage and house type the first and second columns. So we pass, like for the square footage, it should be numeric. So we pass some kind of numeric value here. So this is an integer, this square footage. For the property type for the second column, it is a string, and also we pass basically the most common one, like house, the mode of that column as a default. And for the house price, we just pass it to tell it that this is an integer. So when we pass the recurrent defaulters, basically we are telling it what kind of data it is, the data type. So in our case, it is integer, string, integer.
That's the method.
Yeah, so we have to call this function, and with map here we have parse row that parses the row, each row to features and labels, and this parse row function we are calling it with map here.
Map expects a function that takes records as
right. Yes, and those records, so it is text line, it is a string line, and we want to parse it to the features and columns by specifying the data type.
Where do records come from? There doesn't seem to be a clear continuation from your text line data set to the next line.
So here the text line data set, it reads, what it is doing is it is reading each line from here. So the records are being read here, use the text line data set. So we have the CSV line path, where I am passing the line path, and it is reading the lines line by line. Those values, they are going to be parsed using this function.
But is records really your data set?
I mean, the records is our arguments that I am passing here. I can call it whatever I want.
Right, but my point is that argument is coming from the data set itself.
Yeah,
Yes.
The dot map takes every element inside a data set one
Right.
by one and applies parse row to it.
Right.
So in this case, data set is a collection of records, and parse row is being applied to each record inside a data set.
Yeah, there is the same approach also in Spark RDD. So you pass some kind of records, and you are doing one-to-one mapping when you use map, using some function. Like for example, if you have integers and if you want to square them, if you have a function that squares, you just use map and pass the function name. So once here using the decode CSV, once we specify the default values. Okay, once we specify the default values, so from here I know that the first and the second columns are the features. So that is why I'm creating a dictionary here. Square footage is the column name, and it is the first column. Type is the second column I'm specifying here, and the label should be the last one, or column 3, because Python is 0 indexed basically. So this one. Now once I create this, I return features and label. So such kind of mapping is being implemented here. Once I create the features and labels from each record. Okay, welcome.
Hello, thank you.
So yeah, so we are talking about how to train models using data out of memory, large data sets. Not
TF record.
TF record is one as an example, one kind of data type, but generally where the data is in disk rather than loading it to memory. Like last time we talked about using pandas or NumPy. But now, what if the data is very huge and where you cannot load it to memory? So we are seeing an example of how to do that. Like we started with reading large CSV files. So if we have CSV files, this is what we do. Last time we talked about this. If we start with this, with the bottom here, if we instantiate a model, then we use model.train and pass to that the input function that feeds data to the graph. But in our case, since the data is in disk, rather since it is not a pandas data frame or NumPy array, we use tfdata.textLine dataset. In this case, we have this tfdata textLine dataset. So this one, what it is doing is it is reading each line from the data. So in our last example, if we have such kind of records where we were trying to predict house price, so each row is square footage, property type, and price. So the text line dataset reads every row, and we have to parse the row into features and columns, and we use map with this parse row function to parse the row record into features and label. And to parse the row, we are using this function. So what we do is we use tf decode CSV function, and we have to pass the default values for the records, for each record that we have. Like in our case, the first column is an integer, the second column is a string, the third column is an integer. So we are passing the default values here. So tf decode CSV with records and the default values. Then after that, we create features. What are the features? So the features, we said they should be a dictionary, and in our case, the first column and the second column are the features, and the last column is a level. So we are mapping it basically. All the shuffle, repeat, and batch are the same as what we talked last time. Okay, so we can do any kind of arbitrary transformations with map. So map is basically the same as the map we use in Spark, with Spark RTDs. We can use any kind of transformations with it. So in our case, the map, it creates features and columns from each record, from each row, basically. So what is the input function? Let's understand this, what the input function is doing in our case. And let's see TF estimator linear regressor as an example. How to kind of minimize this maybe. Yeah, okay. So when we instantiate TF estimator linear regressor, it creates this graph for us. First time we call this, the first time we instantiate this graph is being created for us. We said it is linear regressor. So for a linear regressor, it expects some features and a level, and the TF variable is it gets instantiated, and these are the weights. So there is some matrix multiplication and subtraction with the level. So we have from the TF multiplication, we have predicted values, and we have from the level observations. So some subtraction will be done here, and then after it will aggregating it will give us a price and loss. So when we call TF estimator.linear regressor, it creates this graph for us basically. And to this graph, the input function, it passes the features and the levels. This input function, it passes the data basically, and it gets run once. And when we run the graph, the node outputs batches of data to it, and the entire graph is run in a loop basically. So this is what is happening with the input function. It returns the data to our graph that we instantiated using a pre-built model. And when we are dealing with large data sets, out of memory data sets, most of the time our data gets sharded into multiple files. So the dataset API, it handles multiple files as well. And how do we do that? So for that, we use the parse row function. This one is the same. The only thing is we use flat map. This is also, the flat map here is also the same as the flat map we use with Spark RTD. So flat map and map, the difference is map, it creates one-to-one mapping, whereas flat map, it creates one-to-many mapping. So for example, if you have list of lists, the flat map, it flattens it. So it gives you many values from a single entry. So why are we using flat map here? So from the sharded files, from each file, it will read many lines, and the many lines will be from one file, many lines will be a list. And so since we are reading many files, we have list of lists. And when we flatten it, it will create many lines in a single list, basically. So here, first, we create list of the files from the path. We use list files with some, we specify the path, or we can use some wildcard. For example, train *.csv or something. Then we use flat map. And finally, we use map. Like when it is a single file, we used map without the flat map, and this one was here. But now first we create a list of all the files, we create a flat map, we flatten it, and then finally we map it to create the features and columns, the features and label columns. And then all the shuffle, repeat, and batch are the same as before. So in this case, our path is, for example, train CSV. Since the data is sharded, dash asterisk here. We are just passing this wildcard, and it creates all the data, list of all the data files that have this pattern, and it flattens it, and creates the features and label columns. Then the train and the predict is the same as what we talked last time. And also, by the way, this is not used only for flattening the data. We can use any kind of transformations to it. For example, if our data has header, we can skip the header. As you can see from here, we have skip. Add a couple of maps and flat maps. In this map, the other thing we are doing is, if we have preprocess function, we are preprocessing the features here. And once we do all these kinds of chain analysis up to this, we can also do some filtering to include only those that are valid if we have isValid function. So it is really beneficial to use a dataset API. And now let's talk about distributed training if we are using Cloud ML engine. So we have talked about training using data out of memory, and now we are going to talk about distributed training in Cloud ML engine. So far what we have been doing is, once we instantiate a pre-built model, we use train for training and then predict for making predictions. That is most of the time for toy kind of just exercises that we work on in our local machine, like for academic purposes. But in real world training, we use train and evaluate. The train and evaluate function, it has many advantages, so we are going to see that. If, like for example, if we are training in Cloud ML, it handles the distributed training for us, and also it is used for evaluation and monitoring during training. So what we do is, let's see how we do it. So first we instantiate an estimator, as we have been doing. Estimator, if we want linear regressor, tf.estimator linear regressor, we are instantiating an estimator. Then we use tf.estimator. This estimator, it has train and evaluate function. So the train and evaluate function, it does to, if our machine, if it has multi-core, or if we are in the cloud, it handles distributed training, and also as a function shows, it is train and evaluate. So it also saves the model every some steps, so that we can evaluate our model performance. That's why the word evaluate is there. So how is distributed training done? This slide shows architecture of distributed training. So first, the model gets replicated across many worker nodes. These are the worker nodes. The model has been replicated to all of them, and there is data, batches of data coming to each worker node. And there is another server called parameter server. So to this parameter server, the weights, the gradients are sent. So this parameter server, it updates the weights and sends the updated weights to each worker. So this the dedicated parameter server, it expects the gradient from each worker. So when a worker gives it new gradients, it updates the weights, and the weights that have been updated will be sent to all the worker nodes. And then the worker nodes will work on a different batch of data with the updated weights. So the TF estimator handles distributing the graph, sharing variables, managing workers, handling exceptions or failures, and also creating checkpoints. We don't have to do any kind of coding. Just the TF estimator dot train and evaluate handles everything in this slide for free.
This is across threads on a single server or across multiple servers? Multiple.
Yeah, this is multiple servers. So we have one server for the monitoring them and updating the weights, and the different servers are here.
Each server manages its own threads.
Yeah, it reports to the central parameter server. So the other thing is in when we are training in a distributed environment, we have also to shuffle the files, not only the data, but also the files, because like even if our data has been well shuffled in disk, if we don't shuffle it when we are reading it in, every server, all the servers could be seeing the same kind of data at the same time. So if they are seeing the same data, if they are getting the same data, that means they will return the same weight. And in that case, there is an advantage of distributed computing. So we have to shuffle. We have to make sure that we are shuffling it, and we start by shuffling even the files. If we have sharded files, we shuffle the files also. So we have one shuffle here and another shuffle here. This shuffle is the same as what we discussed last time. This shuffle, it shuffles files. If we have many sharded files, and the flat map and the map are the same as what we have seen before. So how do we do it? Initially, we said we have to create an estimator. If we start with a linear regressor, tf.estimator.linear regressor, we have seen how to create feature columns. The feature columns is a list of the columns that you should expect and what data types they are. And also we pass some configuration, like the configuration could be random seed, for example, for reproducibility and other kinds of configurations. Then this estimator, we pass it to train and evaluate. And also there are other two things that we need: train spec and evaluation spec. Basically, these ones are input functions for the training and evaluation, but also they have some additional parameters that we can pass. So in here we have said config is run config. What is this run config? Let's see. To create the estimator, in the estimator we have run config, and what does it include? It includes the model output directory, because for checkpointing we need this to continue from our last training, or to resume on failure, or to make predictions while the model is being trained. We have to pass the model output directory, and every how many steps do we need to save the logs or the summary, and also every how many steps do you want to save the model output checkpoint steps. So these are the configuration. All these configuration, once we specify them, we pass that to the estimator as a configuration. So now we have this estimator. Once we create the estimator, we need the train spec and evaluation spec. What are they? Let's see one by one. So the train spec, we use from the estimator, there is train spec function. So train spec is equals to tf.estimator train spec. The input function is the same as before, just it passes input data, and we have to use the dataset API in this case, because we are talking about distributed training and the data should not be in memory. Basically, well, probably we are talking about large training with large data sets, and optionally also we can pass the maximum number of steps. So now we have the train spec. Basically, the train spec is the same as the input function, the training input function that we saw last time, as an input function that passes the data to the graph. Now we are done with estimator and the train spec. Let's see what the evaluation spec is. And the evaluation spec is given here. So it is tf.estimator.eval spec. And this one is the same as before. It passes the evaluation data as eval input function. And we have the number of steps and throttle seconds. So this throttle seconds is like the minimum amount of time that the model can be checkpointed. So to be evaluated, so if you don't want it to be frequently evaluated, because for evaluation there is a dedicated server that does that, and if you don't want it to be frequently, to do evaluation very frequently, you can control it using this throttle seconds. So now in the eval spec we have passed the input function for the data and specified how frequently the evaluations should be performed and the batches for the evaluations also. So now we have instantiated the estimator with a configuration. We have also created the train spec that passes the input, the train input data with a number of steps, maximum number of steps. And on this slide we have added the eval spec. We are going to see what the exporters are. The exporters are needed if we are going to deploy the model and if we will use it for serving. If we pass the exporter configuration, then in Cloud ML especially, it is a click away for deploying the model.
So in this setup, we are telling it how many training steps to take rather than giving it a threshold to wait for, and then once it passes that threshold, it's done.
So in here, so for the evaluation, we need it to take 100 batches. These are the steps here. And also for the evaluation, we need it to be, so yeah, it is going to, so the evaluation, it will be the minimum of this and this basically. So even if it has done 100 batches, if it is not 10 minutes yet, it will not evaluate it. It will not give you evaluations. This throttle seconds, it helps you to control how frequently it should be done.
So that's checkpoint, right?
Yes. Not only checkpoint. It is not checkpoint. It also gives you not only saving the model, but also like displaying the metrics if you are using TensorFlow.
Yeah. So that's graphic output. My question was more about the estimator itself.
Okay.
So within the estimator, let's say it's just we're doing a linear regression.
Yes.
So typically,
let me go to the estimator. Okay, where was it? Yeah, okay. Yeah, it is here. Okay.
yeah, okay.
So this is the estimator. The TF estimator linear regressor will create a graph, and to that graph we are passing some additional configurations.
Okay. So typically, like not a TensorFlow setup, what you're doing with linear regressor is that you have those weights and it starts minimizing that loss function.
Right.
Until you pass the threshold, and you're like, okay, given a threshold, I'm good. Let's. You're talking about early stopping.
Right. No, about the tolerance.
Criteria.
The tolerance threshold, yeah.
The convergence
Right.
criteria. So
Yeah.
after like a
Yeah.
error.
Here we are controlling it using a number of steps.
Right. So it doesn't have that.
I am not quite sure because we, from the exercises I have seen, we have been specifying the steps.
Taking longer than 1 million steps and stop. Don't go forever.
Right.
I'm guessing there should be an equivalent of this sort of setup.
Probably, yeah, there could be some default value.
With hooks, they have hooks. Like you can have like a training hook that you can add for early stopping. I've seen that before.
Okay. So we can quickly check the documentation, basically. That is what the documentation is for. So if you go to here and go to init here, what do we see? We have feature columns, model directory, label dimension, weight columns, optimizer, configuration, partitioner.
I think you pass the hooks to train and evaluate.
To train and evaluate?
I think so.
Okay. Okay. Yeah, good question. It is something that we have to explore. Yeah.
I remember asking myself the same question.
I see. Okay. Cool. Okay. So in that case, does it mean it doesn't do the iteration up to the number of steps you have specified if it reaches the tolerance value? Okay. Interesting. Okay.
So You might even be able to do like in the function, in the input function, you know, repeat none so that it infinitely repeats.
Yeah.
And it's just terminated by the hook, so there's no need to specify steps.
I see. Okay. So the repeat none, what I know is the repeat none, it indefinitely repeats, but you control it using the number of steps.
Exactly. So what I'm saying is like instead of controlling
The number of steps.
you use the hook.
Okay. Okay. Cool. Okay. Okay. Thanks. So we were here. We have seen the eval spec. So this looks like all the code that we have been talking so far. We specify the run configuration with the model output directory, then pass that to the estimator when we instantiate the estimator. Remember the feature columns here. Then we have the train spec and evaluation spec. The export, we are going to talk what it is later. Then once we have this, we just call the train and evaluate in tf.estimator.train and evaluate and pass all these things that we have created so far. What about evaluation during training? Yeah, we said the train and evaluate method, it handles evaluation during training, and TensorBoard is handy for that. It helps us to visualize what it is doing. And here is an example of TensorBoard showing the results. So the first one here is accuracy. As you can see, the accuracy is increasing, and after some time it has flattened. Here we have the orange color is the training loss or the training error, like for example how it shows how good the model is learning over time, and it looks very noisy. Probably it could be the data type, or I don't know, I mean the batch size or something. But the evaluation loss, it is steadily decreasing up to this, and it has flattened. It is like a mirror reflection of the accuracy basically. And in this example also, I think the learning rate, they have made it to gradually decrease as the number of as the model trains more, which is recommended rather than using a single value for the learning rate. Making it to gradually decrease helps for the model to quickly converge.
Just because, like, if you picture like gradient descent,
yeah,
first taking bigger steps, and then once it's
right,
closer and closer, you want to take smaller steps to
yeah,
the valley.
That's right. Yeah. Final, towards the end, it is optimizing very small kind of curves. And
this is doing the evaluation of the training set as well. So this is a sample.
Yes, both on the training and evaluation data. Because we specified the train spec and evaluation spec that pass both the input function, the input functions for the training and evaluation data sets. So it gives us metrics on both the data sets. Yeah. So and also, the model is being trained. What it is doing is just it uses most recent. There are ways either to pass the most recent weights, or we are going to see in the next slide is which weights to use. And TensorBoard, we can use it with our local machine. So how do we do it? Because when we create the estimator, we have specified the model directory. So tf estimator run config, we have this model directory that we specified. And to TensorBoard, we can tell it where the model output is, just using this single line of code. And TensorBoard gets launched in a local host, 6060 port number, I think. And the other advantage of TensorBoard is also it gives us a graph, the sequence of operations, what kind of operations it is doing, and this helps us to understand if we are doing things the right way, or to debug if there is some kind of error. And finally is deployment, if you are working in CloudML actually. And the exporter is used for that in the eval spec. We have to specify this one. And the exporter here, it expects its own export, like export argument. So here we have tf.estimator.latest exporter. In this case, we are exporting the latest weights, the latest model. We can also export the best model. There is also tf.estimator.best exporter, there is also final exporter. So we use that, but to this one we pass another function, serving input receiver function. So we have talked about training input function that passes the training data, evaluation input function that passes the evaluation data, and there is serving input receiver function. This is like a graph that tells the model what's the input data, what kind of input data it should expect. Then once we pass the input data, it gives us predictions based on the graph that it has created.
So, by the way, TensorFlow serving is a tool that they have for serving your models. You can use like a web API, for example, and query it, hit it with REST. Like you use a REST API to get results back from the model. And so this serving input function is basically what's going to be processing your raw data, and presumably it looks something like your training and evaluation function. But so you have an image, for example, and maybe it does some pre-processing that actually you already did on the training and evaluation set.
Yeah.
So maybe it'll do some additional pre-processing, compress
Right.
it to a certain size, and then run your feature extraction routine, and then feed it
Easy.
into the neural network.
Yeah, we will say an example. That's right. Basically, this part, it is very similar to Amazon's SageMaker
Really?
environment. Yeah. In SageMaker also, once you train a model, you just click it and it deploys it, and it gives you an endpoint. And using that endpoint, once you process the data to look like what the model should expect, then it gives you predictions, and you can use it from anywhere. The SageMaker?
That's SageMaker is
Amazon.
Yeah.
It is just Jupyter.
Microsoft has the equivalent.
Okay, okay.
HD Insight, I think.
Okay, yeah. So all of them have something similar. I mean, there are slight differences and different names, but basically they do the same thing, more or less. So let's see what the exporter look like. So let's start from here. When we are, like for example, when we instantiate a model tf.estimator.linear regressor, it creates this graph, right, for us. It creates this graph. And, oh, by the way, is it visible, sir? Yeah. So, yeah, okay. So we have this, the TF estimator linear regressor, it creates this graph for us. And the training input function, it creates this sequence of data operations, this graph. So the graph from the TF estimator linear regressor, it expects the data from here. It is getting the data from here. The same thing during inference in ML engine, we have this graph, and to this graph, the serving input function, it processes the data. But the difference is, in training input function, in this case, we use CSV data. But now during serving, it expects JSON data. So that JSON data, it reads its values and transforms it. And basically, at the end, it should be in the format. These features, they should be in the same format as these features. So we can do whatever kind of transformations we want, but they should match. Basically, the column names and the data type and additional kind of transformations or feature engineering we do, we have to include to both of them. Okay, so how does this node, how is it reading the JSON data and processing, transforming it? Let's see. So we have here an example. Serving input function, in our case, since we are creating the house prediction. So first we create placeholders. So this placeholder with the features, square footage and property type. The square footage is int, the property type is a string, and putting this none, I was not aware of this putting none inside a list, inside this square brackets, is like it helps you to pass both a single value and also batch of values. Yeah, the placeholder, it is telling the placeholder to expect one or more values basically. So from this JSON, then what we are doing is we are creating the features. these features are in the same format as the features we saw during our training. So JSON, the square footage, from the JSON we are extracting it here, and the property type also. Now once we do this, we return it as tf.estimator export. The function names are very long and weird at times. tf.estimator.export.serving input receiver, and we pass the JSON and features. So to the latest export, now we have this latest exporter. We are giving it a name because it is going to save the model. So we need, it is good if it is a good practice if we give it a name to know which one is which. Then we pass the serving input function that we have created here. So this serving input function, it is the same, similar to the training input function we are doing with CSV data, but this one is batch, and it is for also this is JSON, and also it is for inference. So we create first placeholders because this is JSON data. It has to read and process JSON data. So create placeholders. The placeholders expect a single value or more than one or more values, and create from the JSON features, and this serving input function we pass it to the exporter. Now we are done with the eval spec, because now the eval spec has exporter as well. So when we run it, it is going to export the model, save it in Cloud ML, and we are going to see the saved model, and we can just click it and deploy it, and it gives us the API for inference. So here it shows, because we call it pricing, it shows us the saved model is here, and we can deploy it from here. And if we are in Cloud ML environment, in Cloud ML, let's see how to test it locally first before even we deploy it. We can just test it using by pointing it to the saved model output directory. So this is our saved model. But first, what we do is, for testing, we have to create a JSON object where each record is its own row. So we have square footage and property type. The second row also square footage and property type. So once we save this as a JSON, let's say we save it test.json.txt, then we can test a model using Cloud ML engine local predict, and specify the model directory, and tell it the JSON instances. Whereas what is the JSON instances that we have it locally, and it is text json.txt. So it gives us prediction from these values. And also we can use it, we can test it after we deploy our model. So in that case, for the data we create a JSON field of instances, and the JSON field of instances, it contains JSON objects of the features here, and we can, using the REST API, pass this and give it a model name. So once we give it a model name and pass the JSON instances, it gives us predictions. Is this similar to to Microsoft's Insight data? Is it called Data Insights? Does it have similar kind of?
I've never looked into it. I've only read about this.
Okay.
But one thing I will say is that there's something called MLB, which I believe SageMaker might be using. Last time I looked at SageMaker, it used that basically to package up whatever feature extraction routines you're doing, and also like could be TensorFlow, or could be like MLlib.
Okay, yeah, that is available in SageMaker, but I'm not sure if it is available in TensorFlow. Yeah, I will explore it. Good point. Yeah. So this is how we do it. Basically, in a real-world environment, we use today's approach, like using data out of memory and distributed environment, if you have that kind of environment, saving and checkpointing and testing also. And this is all for today. Next week we are going to talk about how to process image data and time series data using convolutional neural networks, and also how easy it is to use Keras with TensorFlow. Actually, if we are using Keras inside TensorFlow, it is very intuitive. It is like old English, and I like that. So I'm going to talk about that next week. Thank you very much for today.
Thanks, Christian.
Thank you.
Thanks.
Thank you.
You're welcome. Thank you. So.